Good morning, students.
Good morning, sir.
Good morning.
Hope all of you have appeared the test the last Thursday.
Yes, sir.
Okay, we'll start our class today. A little bit delayed, but I'm just booting it up. Today is 25. Yeah, let me share this screen. Yeah. Hope you can see the screen.
Yes, sir.
Yes, sir.
Okay, we'll start. So in the previous classes we have seen the projections. We'll utilize the projection now. How to utilize the projection. And the utilization of projection, this is actually the very first step. Utilization of projection is the very first step in all your machine learning steps. How do they utilize the projection? We'll take a simple example today. In the next class, we'll see much complex examples. Today, let it be a very simple example. Okay. So, okay. This is how bad it is. Okay. I have my x-axis.
Sir, can you please start the recording?
Oh, yeah. I forgot. So this is my x-axis, this is my y-axis, okay, and we have a couple of points. Let us say the couple of points be somewhere here. Let me zoom it a little bit. Yeah, zoomed a bit away. So what is that? Yeah, I have this is my x, this is my y. I have few points here. Let us say here 1 point, here 1 point, like that. Couple of points are there. Now I have deliberately taken the x coordinate at regular interval. Okay, I have deliberately taken x coordinate at a regular or irregular interval also, but then very much determined. And the y coordinates are the noisy coordinates. So x value are correct and corresponding y values are noisy. A very common scenario that you will find data science problem, machine learning problem, and you are asked to fit a line. You are asked to fit a line that has all these points with it. Now, there are a couple of scenarios like I can take majority of the points and fix a line and leave the other points. I can take 2 or 3 points. 2 points is correct, right? Using 2 points, I can prepare a line. I can draw a line. So let me draw using 2 points and leave the rest of the points. So using those 2 points, whatever line I draw, that is the most accurate line. But then I am allowing to incur huge amount of losses that is being caused by the other points. So that is actually not required. That is actually, I mean, avoided. So what is best thing that is being done is draw a line that has that has got, I mean, the that represents the all the points. It's not that I will be biased towards couple of points and leave the rest of the points. It should not be in that way. I should draw a line that should represent all the points. So here the data points are like x1, y1, x2, y2, and so on. Then points should be represented. And your line equation is y is equal to mx plus c. C stands for the y-intercept, m is the slope. So y is equal to mx plus c. This is what the equation is. So if I want to draw the line, I mean using all the data points, so this becomes y1 is equal to m times x1 plus c, y2 is equal to m times x2 plus c. This is how the equation would be, right? Yn is equal to m times xn plus c. Now, this particular equation, if I represent using a matrix form, this would go something like this: y1, y2, yn. Is equal to m times x1 plus c, m times x2 plus c, or so to say m times x1 plus c times 1. In that way I can represent. So let me write in this way. Here, what are the unknowns? Here, what are the unknowns in this equation? What is the unknown?
M and C.
That's right. M and C are the unknowns. So we have two unknowns. We have two unknowns, M and C. So this is a matrix of 2 cross 1. So this has to be, the number of columns has to be 2, and number of rows will be the number of equations. So the number of equations here we have n number of equations we have. So let me write this one as x1, x2, xn. So n number of rows and 2 number of columns. The second column will be 1. So this actually represent the very famous equation B is equal to AX, isn't it? B is equal to AX. This is what it represents. Now, how many variables we have? 2, M and C. How many equations we have? N. If 2 is way less than N, or the number of equations are much larger than the number of variables, what situation we call this one as? This we call it as overdetermined situation. Overdetermined. And here the solution that you get, solutions are inconsistent. The solutions that we get are the inconsistent solutions. That's right. What is this? 2? No, this is something. Yeah. Okay. Okay. So from the vector point of view, what we obtain, what we understand from the vector point of view, B, the vector B, vector B has to be in the column space of A. But in overdetermined situation, this is not possible. So B is not in the column space of A. If B has to be in the column space of A, if this is true, if this is true, then you have new solutions. If it is false, this becomes inconsistent. What happened? Yeah, this become inconsistent. So in overdetermined solution, B is actually not in the column space of A. So what is to be done? Our job here is to project B onto A and get the difference of B minus X as minimum as possible. And that is what we have been seeing in last two classes. This is what we have been seeing in last two classes. Our job here is to project V2 onto U1 and get this projection P so that this right angle vector E error vector, this becomes as minimum as possible. And the same thing will be done here also. B will be projected to the vector A. That is how this entire line fitting, curve fitting is about. This is what we call as least square solutions. We'll talk about this today, least square solutions. Okay, so let us take an example. Let us take an example. Let me have a couple of equations, like let me have x equal to b1, 3x, let me take all the odd numbers, 2, 5x equal to b3, then I have 9x equal to b4. So I have 4 points and 4 equations, 4 corresponding line equations. I want to find out a representative line or the least square from among all this. So one of the, this particular equation is solvable only here how many variables are there? So only one variable x. So this b1, b2, b3, b4, these are all solvable only when you have b1, b2, b3, b4 all are in the ratio of 1:3:5:9. Then the solution x will exist. What does that mean? The matrix A, the column space A and the space of B, they all lie in the same line. Or so to say, B is in the column space of A. If B becomes 1:3:5:9 here in this particular example, then B is said to be in the column space of A and you get a consistent solution. But that doesn't happen. That doesn't happen. So what are the alternatives we have? The alternatives is squared error. Find the squared error. What is the squared error? Let's go for this. X minus b1 square plus 3x minus b2 square plus 5x minus b3 square plus 9x minus b4 square should be as least as possible. Let me call this one as error E. As these are all squares, let me put here this also square. So what is the minimum error is? Minimum error is E equal to 0. That is what the minimum most error. So well, you know this fact, right? Derivative, the first derivative, uh, you equated the first derivative of this equation to 0 and solve it. That is the point where you get x as the minimum, right? So let us find the derivative. Here in this case, d e square by dx. D e square by dx. How much it would be? 2 times x minus b1 into 1, 2 times, sometimes it doesn't respond properly. Here, just a minute, let me wear the clothes. Just a second. Yeah, in the meantime, you can calculate what is the derivative here. 2 times 2 times x minus b1 and derivative of x minus b1 is 1. So 2, 1 plus 2 times 3x minus b2 to 3 plus 2 times 5x minus b3 into 5 plus 2 times 9x minus b4 into 9. and this has to be equal to 0. And solving for x, the least square solution of this system of equations, this is what you get. So what is x now? What is x? X is equal to this, all these two, if I take common and divide it by 0, so that vanishes. So what is remaining is x minus b1, 3x minus b2 into 3, 5 times 5x minus b3, and 9 times 9x minus b4. That is what it remains. So if I take all the, if I take the x on one side, so what is x? I have x minus b1 plus uh, 3 into 3 into x minus b2, 3 into b2. What is 3 into b2 plus 5 times 5 times x minus 5 times b3 plus 9 times 9 times x minus 9 times b4 is equal to 0. This x, let me write it as 1 time x. So x becomes, and this also let me write 1 times b1. So this, all this b1 with coefficients are negative, so there they go, becomes positive. So 1 times b1 plus 3 times b2 plus 5 times b3 plus 9 times b4 divided by 1 times 1 plus 3 times 3 plus 5 times 5 plus 9 times 9. What is this? What is this? One, 3, 5, 9, 1, 3, 5, 9, B1, B2, B3, B4 divided by 1, sorry, not 1, 1, 5, 9, 1, 3, 5, 9. Does it look familiar to you now? Does it look familiar? Can I write like this? A transpose B upon A transpose A. And let me not write this as X. Why? Because this is an estimate of X. This is not the exact solution you will get ultimately. So let me put this one as X cap. This is an estimate of X. So this is what you get. And this is what is your least square solution. So the derivative of E square is 0 at this particular point. At X cap, the derivative of E square is 0. So what exactly we are doing here? We are actually minimizing the distance from the vector B onto a line A. And that is what we have been doing in the last couple of classes. We're trying to minimize, we're trying to find the projection of a vector B onto the line A. And that is what the minimum distance. And here also the same thing. We are minimizing the distance from the vector B by drawing a projection onto A. And it's what uh, so this is what the least square solution to a problem y equal to ax equal to b, least square solution to ax equal to b with one variable, of course. With one variable. And if you recall, let us see that where to recall. This particular vector, what is that called? E vector, error vector. E is equal to V2 minus P, right? Or B minus this P is equal to escape A. This P is equal to escape A. Somewhere we have written. No, in the previous class. Projection matrix. P is equal to escape A. P is equal to escape A. This is what we got. P is equal to escape A. And this projection C is equal to B minus P. This is what we have written. And P is equal to escape A. And this is what the error term is. So the same thing we'll put it here and let us see how they behave. So we have one vector as A We have one vector as A and another vector as error vector E. These two should be orthogonal. So what is E? E is equal to B minus P. And what is P? X cap A. So A has to be perpendicular to B minus XA. So that is A transpose B minus X cap A should be equal to 0. So this becomes A transpose B minus A transpose X cap A. What is X cap A? A transpose B upon A transpose A. That is what X cap is? A transpose A, which is equal to 0. So this is what the least square solution for one variable. We'll stop here today. Next class we'll talk about more variables. Okay. So, by the way, how was the exam?
Good, sir.
It was.
So
Hello,
Sir,
sir.
I
can
had
you
a
find
doubt.
our solutions?
Hello.
Yes, yes.
Sir, when we have a matrix, one-dimensional matrix, like if the values are in one row, are they in same direction, or is it like if they are in same column, then they are in same direction?
No, I didn't get you. Can you repeat the question once again?
Sir, if we have a horizontal matrix, one-dimensional, one row, then all the
Yes.
values are in same direction, or is it like if we have a vertical matrix, one column, then all the values are in same direction? Like the direction is row wise or column wise?
Well, we write Ax equal to B. In that way, Ax equal to B, the rows of A times the columns of B, rows of A times the column of X equal to B. So that forms one line. That forms one straight line. Similarly, the second row of A to the column of is equal to B, that forms the second line.
If we have one row, three values suppose, so all the three values in that row belong to different directions.
Yes,
Okay.
three vector, one vector, three components are there. One row,
Yes.
that's a row matrix, right?
Yeah.
Yes, yes, yes. If it's a column matrix, then we call it as a vector.
So to find the
And
norm of a row matrix, we will use the formula x square plus y square plus z square whole root over. And for a column, we will add them up together because they are all in the same direction.
well, generally we represent a vector using a column matrix. Okay, and we find the distance of the vector by squaring those values, sum that up, square root. That is what the distance it is found. Now, in what way you put the convention, that is up to you. The convention says that the column matrix is a vector. Generally, we represent a vector using a column matrix. Now you want to represent, you want to put it, you have a row matrix. That means it is assumed that you have 2 columns or 3 columns in that matrix. In that way, it has to be treated.
So if it is a column, we take every value, square them up, add, and then root over. And if it is a row matrix, then we take the absolute value of the sum.
In that case, I mean, most of the cases generally, I mean, invariably we write this row column interchangeably. So that way it will be done.
Confusion since nothing was mentioned particularly. So I just thought row matrix will be in the same direction, and that means we will add them all up to find the norm, find the magnitude. And for a column matrix, I thought they are in different directions, so I will take the sum of the square roots.
Why do you want to represent that in the column row matrix then? Okay, we'll talk about this.
Sir,
Uh-huh.
could you provide a solution for the exam you took so that we could tally our answers?
Just a minute. Let me publish it itself.
Hello, sir. Hello.
Yes.
I forgot to submit in due time. Could you reopen the portal?
Portal reopening. Yeah, we can do that. If it is possible, I can do
Yes,
that.
I have a solution with me. I just take a few minutes to submit it.
I'll try to open it. I will try to open it. Anything else? Let me check how to open this. Mhm. Yeah, how many such students are there who haven't submitted? I can see there are so the eight students are there. Okay. Well, I have updated the due date. I may submit it. Well then, we'll call it a day. Bye.